NVIDIA just dropped something that basically rewrites how vision models work. And honestly, the young community is still catching up to what this actually means. We're talking about C-RADIo V4, a vision backbone that takes three of the most powerful vision models ever built, Siglit 2, Dino V3, and SAM3, and distills all of them into a single encoder that handles classification, dense prediction, and segmentation workloads at the same time. And the crazy part is that it does this while using an order of magnitude fewer parameters than the teacher models. This is not some research experiment sitting in a lab. The model is available right now on Hugging Face, fully open for commercial use, and it's already replacing vision encoders in production systems. So let's talk about it. Alright, so the first thing to understand is what NVIDIA actually built here. C-RADIo V4 is an agglomerative vision backbone, which means it takes knowledge from multiple specialist models and combines them into one student model that inherits all their strength. This is not a new concept. The radio family started back in 2024 with AM radio, then evolved through Radio V 2.5 and C-RADIo V3. But C-RADIo V4 takes the entire approach to a completely different level by updating the teacher set and fixing the biggest problems that plagued earlier versions. The model comes in two variants. C-RADIo V4H, which packs 631 million parameters, and C-RADIo V4 SO400M, which sits at 412 million parameters according to the official technical paper. Now here is something interesting. The Hugging Face model cards list these as 653 million and 431 million parameters, but the RC paper consistently states 412 and 631 parameters across multiple sections. So there is a small discrepancy between the model card and the official research report. Both variants were trained on around 700 million images using a stochastic multi-resolution training approach that covers anything from 128 pixels all the way up to 1152 pixels. And here's the thing that really matters. These models are not just competitive with the teachers. In some benchmarks, they actually beat them while running faster and using way less compute. Now, let's talk about the teacher models, because the upgrade here is massive. The previous version, C-RADIo V3, distilled from DFN clip, Dino V2 and SAM. But C-RADIo V4 swaps in three newer, more powerful teachers. Siglip 2G384, which handles text alignment and zero-shot classification. Dino V3G, Meta's self-supervised vision giant, trained on 1.7 billion images that absolutely dominates dense predictions task. And SAM3, Meta's latest segmentation model that can detect and segment 270,000 unique concepts using text prompts and reaches 75 to 80% of human performance on a essay core benchmark. Each of these teachers is a powerhouse on its own. Dino V3G achieves 63.0 mean intersection over union on ADA20K semantic segmentation and 66.1 mean average precision on COCO object detection with a frozen backbone. SAM3 introduces text-based promptable concept segmentation, which means you can type "Yellow school bus" and it finds every single instance in an image or video. Siglip 2 brings that crucial text alignment that makes vision language models work, and C-RADIo V4 distills all three into a single model that weighs a fraction of what you would need if you ran all three teachers separately. Here is where it gets technically interesting. NVIDIA did not just throw these teachers together and hope for the best. They introduced 4 key techniques to make this distillation actually work at scale. The first piece is stochastic multi-resolution training. Instead of training on fixed resolutions like 224 or 384 pixels, C-RADIo V4 trains across a continuous range from 128 to 1152 pixels. This smooths the performance curve across resolutions and fixes one of the biggest problems in earlier radio models, where performance would collapse at certain resolution thresholds. The model learns to handle any input size within that range, which means you can throw 320 pixel images, 768 pixel images or 1024 pixel images at it and get consistent high quality features without retraining or fine-tuning. The second technique is called shift equivalent Dane's loss. This one solves a problem that has hunted vision model distillation for years. When you distill from large models like Siglip 2 or SAM3, you do not just copy their useful features, you also copy their artifacts, border noise, window boundary patterns, position fixed glitches. Direct feature regression forces the student to memorize these problems instead of learning the actual semantics. C-RADIov4 fixes this by showing the teacher and student different shifted crops of the same image. Before computing the loss, it aligns the features using a shift mapping and only compares overlapping spatial positions. Because the student never sees the same absolute positions as the teacher, it cannot memorize position-based noise. It has to track the input-dependent structure instead. The third piece is shift equivariate MESA. MESA stands for mean exponential moving average stabilization, and it is a regularization technique that compares the student network to a slowly updated copy of itself. C-RADIov4 applies this with shifted crops again, so the students and its EMA copy see different views of the same image. After layer normalization, the loss gets applied between aligned features. This encourages smooth loss landscapes and makes the model robust to distribution shifts without getting tapped in position-specific patterns. The fourth technique is called balanced multi-teacher distillation with angular dispersion normalization. And honestly, this one is brilliant. When you distill from multiple teachers using standard cosine distance loss, teachers with wider angular dispersion dominate the optimization. Siglip 2 produces embeddings concentrated in a narrow cone on the unit sphere. Dino V3 spreads its embeddings much wider. If you just use raw cohesion distance, Dino V3 contributes larger losses and drowns out Siglip 2's contribution. C-RADIov4 fixes this by normalizing each teacher's loss by its own angular dispersion. This equalizes the contribution from Siglip 2 and Dino V3, preserving both text alignment and dense representation quality at the same time. Now let's talk numbers, because the benchmarks are where this really proves itself. On ImageNet 1K0 short classification, C-RADIov4 hits 83.09% top 1 accuracy. That matches or improves on RADIO-V 2.5H and C-RADIO-V3H across all resolutions with peak performance near 1024 pixels. For K nearest neighbors classification, C-RADIO-V4 reaches 86.68% accuracy on ImageNet and starting at 256 pixels, it matches or surpasses Dino V3. On semantic segmentation, the gains are even more impressive. C-RADIO-V4 reaches 55.20% mean LOU on ADA20K using just a linear probe on frozen features. Dino V3G sits at 63.0% on the same benchmark. So C-RADIO-V4 gets within about 8 percentage points while using dramatically fewer parameters and running significantly faster. On Pascal Vox semantic segmentation, C-RADIO-V4 achieves 87.24% mean LOU, which is another strong showing for a model this efficient. The real breakthrough though is the any resolution behavior. Previous agglomerative models like AM radio suffer from mode switching. They would produce Dino-like features at low resolutions and SAM-like features at high resolutions. This inconsistency made them unreliable for production use. C-RADIO-V4 solves this through multi-resolution training combined with feed-surf upsampling for Siglip 2. Siglip 2 operates natively at 384 pixels. C-RADIO-V4 upsamples those features by 3 times using feed-surf to align with SAM3's 1152 pixel feature. This design stabilizes performance across the entire resolution range and prevents the model from collapsing into different models depending on input type. Another major upgrade is white date mode support. This is huge for deployment because it allows most transformer blocks to operate in windowed attention mode instead of full global attention. Windowed attention dramatically reduces computational cost at high resolution without destroying accuracy. C-Radio V4 supports window sizes from 6 by 6 tokens all the way up to 32 by 32 tokens, as long as they divide evenly with the patch size and image resolution. On an A100 GPU, the SO400M model with window size at most 12 is faster than the SAM3 White L class encoder across a wide range of input sizes. The huge model with window size 8 is close in latency. This makes C-Radio V4 a practical backbone for high-resolution dense tasks where full global attention at every layer is too expensive. And here is the part that really caught everyone's attention. C-Radio V4 is a drop-in replacement for the vision encoder in SAM3. The SAM3 decoder and memory components stay exactly the same. You just swap out the vision encoder backbone with C-Radio V4 and segmentation behavior in out. NVIDIA even provides a reference implementation in a SAM3 fork showing exactly how to do this. Qualitative examples show that segmentation works for both text prompts like show, helmet, bike, spectator, and box prompts. And in some cases, C-Radio V4 based SAM3 actually resolves failure modes from the original encoder. The slight difference in representations between the two vision encoders appears to improve robustness on certain queries that struggle with the default SAM3 backbone. Now, to be clear, C-Radio V4 is not perfect. SAM3 as a teaser does not show improved metrics on the selected benchmarks compared to earlier teasers. NVIDIA includes it specifically to enable SAM3 integration and to support creative use cases like RADSEC, which is an open vocabulary semantic segmentation framework that posts state-of-the-art results in both 2D and 3D domains using agglomerative models. Another limitation is the wide date mode with small window sizes can degrade accuracy slightly on tasks that require long-range spatial dependencies. But for most practical deployments, the speed gains massively overweight the measured accuracy drop. The licensing story also matters here. C-Radio V4 is governed by the NVIDIA Open Model License Agreement, which enables both commercial and non-commercial use. This is a big deal because it means companies can deploy this directly into products without worrying about research on the restrictions. The model is available on Hugging Face under the NVIDIA Radio collection, and you can load it via Torch Hub or the Transformers library in about 5 lines of code. NVIDIA also integrated C-Radio V4 into Tau Toolkit, which is their training, adapting, and optimizing framework. This means you can fine-tune C-Radio V4 for domain-specific tasks using Tao's pipelines without rebuilding infrastructure from scratch. One of the most interesting applications already emerging is in vision language models. C-Radio V2 VLM, which is powered by an earlier radio variant, currently ranks number 1 on OCR Bench V2. That model uses feed-surf for feature sharpening and a carefully tuned distillation process. C-Radio V4 inherits those same techniques and adds stronger teachers, which means future vision language models built on C-Radio V4 could push even further on multimodal benchmarks. Models like Llama Nemotron Nano VL already use radio-based vision encoders, and switching to C-Radio V4 would likely boost performance on tasks that require both text understanding and dense visual grounding. Another area where C-Radio V4 shines is retrieval. Dino V3 set a high bar on instance retrieval benchmarks, improving over Dino V2 by significant margins. C-Radio V4 tracks those improvements closely because it distills Dino V3's dense features into a smaller, faster backbone. For applications like image search, product recommendation, or content moderation, having a single model that handles retrieval, classification, and segmentation simultaneously eliminates the need for multiple specialized pipelines. That is where we will work it up. One thing I am curious about now is how other companies will respond to this because the bar just moved significantly. If NVIDIA can distill 3 state-of-the-art features into a single model that handles everything from classification to segmentation at scale, the next generation of vision models will probably follow the same patterns. Drop your thoughts below. Make sure you are subscribed, hit the like button, and I will see you in the next one.